Hey everyone, welcome back to AP Precalc. This is Mr. Herc, and today we're going to be going over FRQ1. Let's get right into it. Pause the video if you haven't done the bell ringer, because I'm about to go over 3-peat J right now. All right, so here we have a graph of a polynomial function f. Which of these following equations could be a possible expression for f of x? So here, the first thing I notice is there's two zeros, but they're not labeled because the x-axis isn't labeled, so that's really helpful. But looking at the multiple choice answer choices, sometimes we can use these to our advantage. And we see it's in factored form, so that's going to give us information about the zeros. And all four answer choices have the same two linear factors. We see x plus 2, and then we also see x minus 4 for all four answer choices there. X plus 2 is going to imply a 0 at x equals -2, and x minus 4 will imply a 0 at x equals +4 there. So we can fairly assume that those are going to be our two zeros for this graph shown above. Now, one thing that we know about zeros is when they bounce off the x-axis, like at -2, this is going to imply, or we can conclude that this has an even multiplicity. And when they pass straight through the x-axis, like at 4, this is going to imply an odd multiplicity. And remember, the multiplicity is just the degree or the number in the exponent of that linear factor specifically. So at x plus 2, that linear factor, we should see an even number. For A, this is an implied exponent of 1. Same with B. C, there is 2, and D is also 1. So C is going to be our answer just from that. Just to make sure, though, x minus 4 has an implied multiplicity of 1. So that is odd. So both of those check out, making C the correct answer there. All right, number 2, where x is positive, which of the following is equivalent to this? So this is just simplifying or condensing a bunch of logarithms. You're going to have to do this in the free response section. However, you could also see a multiple choice question like this. So let me start by moving any number out front. I just see that 2, and I'm going to move that to the exponent. So I'm going to have ln x plus 3 minus ln, and then this becomes x squared minus ln x plus 4. Now we're going to combine this into one big fraction. So this is going to be ln of a big fraction. And remember, anything with an plus sign, so this x minus or x plus 3, is going to go in the numerator. So let me throw that up there. And anything with a minus sign, in this case we have x squared and x plus 4, will be multiplied in the denominator. So this should be x squared times x plus 4. You could distribute that, but we're just looking for the multiple choice answer, which is also C for number 2 there. All right, number 3, the location of a point in a polar coordinate form is 5, 7 pi over 6. Which of the following gives another representation for this point in polar coordinates? So let's see. Sometimes with these multiple choice questions, we have 4 answer choices, and we can get our answer, the correct answer, from one of these choices without really worrying about the explanation. And you'll see that on probably 2 to 3 exam questions, I would say, on the AP exam every year. So let's take a look and see if we can just get our answer choice just from these points alone. And then if we need to, then we'll look at the explanation behind it. So here, 5, 7 pi over 6 is going to be 7 pi over 6 is right here. And then 5, we'll just say that this is a distance of 5 there. So that's going to be where it's located. And now let's kind of plot where A, B, C, and D are going to be as well. So A here, -5, -5 pi over 6. That's going to be right here. And then -5 goes in the opposite direction. So A is going to look like that in the first quadrant. B, -11 pi over 6 is right here, going 11 pi over 6 this way, and then -5 turns it right here. So B should be our correct answer, but let's take a look at the other answer choices. C, pi over 6, 5, that's just right there in the first quadrant. And then D, 5 pi over 6, 5, That's going to be in the second quadrant. So B is the only one that is in the third quadrant along with the actual coordinate that we were given. And let's just look at the explanation to see if it's right. Because 11 pi over 6 clockwise from the positive x-axis, that's inferring a negative angle measure, lies in the opposite direction of 7 pi over 6. That was a positive angle measure, and the radius is negative. So that makes sense. So B is going to be our answer for number 3 there. All right, so let's get into FRQ1, the notes for today. Basically, the AP exam will consist of 40 multiple choice questions and then 4 multi-part free response questions. These 4 are insanely predictable and basically ask the same questions year after year. And for that reason, I'm going to spend a lot of time preparing you for the exam by focusing on these 4 free response questions. If you can get a majority of points on this, and then just do decent on the multiple choice section, you're almost guaranteed to at least get a 3, possibly a 4 or a 5. So FRQ1 is a type of question that you've definitely seen before on tests and review guides. Basically, it's going to test your ability to know and use different functions. There's 3 different types that you're going to come across, and these will always stay the same. You'll have f or g. F of x will either be an xy table or a graph, so it'll be one or the other. And then g of x will be an equation, guaranteed. It's going to be one of these 4: polynomial, rational, exponential, or logarithmic. So polynomial could be like x squared plus 2x minus 5. Rational could be x over x plus 3. Exponential could be 2 times 0.8 to the power of x. And then logarithmic could be 5 plus 2 log base 3x. All of these are examples of equations you could see. Now, over the course of the next 2 weeks, we'll break down each FRQ question one by one. We'll spend a day for each one. And then those 4 questions will consist of your semester summative. So here, the first one will always be the table or graph. The second one, g of x, will be your equation. Each of these parts may ask about one or both functions, so really pay attention to what function it's asking about. Is it about asking about f or g? Because I've had countless students answer the correct answer just to the wrong function. So just make sure you don't make that mistake. Now, these are the 6 possible questions that they can ask you. Here, for the first 4, each of these could only be 1 point. So composite functions, inverse, using Desmos, and behavior, you will see one of those 4 on every FRQ. And then you'll either see 5 or 6, where these are going to be worth double points. So you've also seen these questions before. Determining the type of function, whether it's linear, quadratic, exponential, or logarithmic, or determining if a function is invertible, or if it has an inverse, or if it's 1-to-1, right? So we'll go through each of these 6, get some practice problems in, and then hopefully that should prepare you for this FRQ along with your homework as well. So number 1, composite functions. The first question will ask you to plug a number into the table or graph first, and it's always going to be first, and then you're going to take that answer and you're going to plug it into the equation. So let's just get a little bit of practice, plug it into just a single function first. So example 1 should be pretty easy. Find the following values of the function f. F of 2, when x is 2, f of 2 should be 4. So here, f of 2 equals 4. F of 5 is also 4. And then f of 1 is, in this case, 6. So we're going to start off, pretty easy. Let's move on. Example number 2, use the following functions of, here it's just j and k. I cut out some of the equations. Define the following values or indicate that it is not defined. So here, you could actually use Desmos for these. So what I would do is have your Desmos screen like this, where you will have access to a graphing calculator for this question. So I would use it on some of these questions. For A, you can literally type in this j of x function into Desmos, even with the j of x. And I would do that because then you can type in j of 0, and get your answer. So in this case, j of 0 would be 1. Now, if we have k of negative 5, right, I typed in k of x, and so that's great. Now remember to get this custom log, right? If you just type in log and then x, this is going to be an implied base 10. If you need this to be any number besides 10, let's say in this case, right, we need a 5. Remember, you're going to go to your keyboard icon, functions, go to the calculus section, and then this button right here will allow you to enter a custom base for a logarithm. So you may see that. So just be prepared to know how to use it. In this case, I typed in k of x, and then I typed in k of negative 5, which is undefined. So just be prepared to see that. This is undefined because if we plug in negative 5, we get 8.7 log base 5. Negative 5 times 2 is negative 10 plus 6.7. This is negative 3.3, which you can't take the log of a negative number. So that's why it's undefined. So sometimes you will see that. I've seen it happen on AP exams before, so just be prepared for that. All right, number 3, find the values of g or indicate that it's not defined. G of 2, this is where x is 2, g of x is going to be equal to 3. G of negative 1, this is when x is negative 1, g of x, that technically has a y value of 0, so that's b. And then g of 1 here, I see at 1, there's a vertical asymptote, so this would be undefined or not defined. So even if it's not defined and there's technically no answer, you still need to state that it's not defined or undefined at that point. All right, so this is the type of question that you're going to see, and this is when we actually have a composite function. So when you have a composite function, plug the number into the inside function first, and then whatever you get as your answer, you're going to plug that into your equation, your outside function. So you'll always have to use the table or graph first, and then plug it into the equation. Let's look at example 4. Here we want to find the value of h of 4, where h of 4 is equal to g of f of 4. Here we need to show the work that leads to your answer. So I would literally write this. From this table, f of 4 is 2. So this is equal to g of 2, which is equal to, and then this is where I would use Desmos to plug 2 into g of x into the equation. So the work I would have shown is I would say h of 4 is equal to g of f of 4 equals g of, and then this was 2, which equals negative 1.06, and then rounding 9. So remember, decimal approximation means 3 decimal points. I will be picky on the semester summative. I don't know how many times I need to say it, but if you do not give me at least 3 decimal points, I will mark it wrong, and this entire question will be no credit, or this part of the question will be no credit. So make sure I get at least 3 decimal places. Here, this should be the correct answer though. So just make sure to show all your work. On their test, I would need to at least see this number 2 somewhere in your work to give you credit. All right, the second type of question I could ask about is inverse functions. Here, you're going to be asked to look for the x values when your y value is a certain number, or to find the inverse of a function. Both basically just give you a y value and ask you to look for your x value. So let's take a look at some of the questions that you could see. Here we have a table, and then we want to find all the values for which f of x equals 4, or indicate that there are no such values. So this may be definitely the case at times. I've seen this be present before. So let's take a look here. Where is f of x equal to 4? Well, I see f of x is 4 at 2 and 5, so I'm going to write that as my answer. X equals 2 and x equals 5. You don't have to show any work, so this would be good enough for full credit. Number 6, find the values for which f of x equals 5. Here, though, if I look at f of x, f of x equals 5, I don't see any time where this is equal to 5, so I'm going to put no such values exist. And that would be enough to get full credit there. Now, this is the other type of form that you could see question number 2 or part 2 coming, which is find the value of the inverse of 6 or indicate that it is not defined. Here, we're using the same table. We see 6 here, so this is just going to be 1. I do not want you to write x equals 1. That is not what I want. I want you to write this. So I will actually take off points if you put x equals 1. But here, just say the inverse of 6 is 1. Or honestly, just be safe and you could just put 1 as your answer. But if you put x equals 1, that will be marked wrong. So do not do that on the semester summative or on the AP exam. Here, find the inverse value of 3 or indicate that it is not defined. There is no 3 right here, so this is going to be not defined. And that would be enough to get full credit for example 7. All right, now if you're using a graph, typically the answer is going to be a very nice clean integer. So let's try example 8. Find all the values for which g of x is equal to 3. Here I would see this is going to be your g of x. And where is this equal to 3? So I would draw that line. That's that point right there, which is where x equals 2. So that's going to be our answer to example 8. Example 9, find all the values for which g of x equals 1. Here, this is a horizontal asymptote, so it will never touch. So I will say no such values. And that would be my answer for example 9. So I'm giving you, it may seem like a lot of cases where it's no such values. I just want to show you what that would look like. But in reality, it is pretty rare that you'll see no such values, but you could see it on the AP exam. All right, number 10, find the inverse of these. So here we're finding the inverse of g of 3. This is going to be the same thing. So when g of x equals 3, that's when x is 2. So the inverse of 3 will be equal to 2 there. So it's the same question as example number 8, essentially. Part B, 10b, will be basically, where is this going to be equal to -1, though, not +1, so I did switch that up. Here, this is equal to -1 at x equals 0. So I'm going to say inverse of -1 equals 0, and that's going to be my answer for example number 10. All right, number 3, using Desmos to find the zeros or intersection points. So the next question will always be asking about the equation, and we'll ask you to use Desmos or your graphing calculator to find either points of intersection or zeros on a graph. And so it's pretty much just a matter of typing the equation into Desmos. So let's take a look at a few example problems. Example 11, the function g is given by that polynomial. Find all real zeros as decimal approximations. So remember here, when they say decimal approximations, that means 3 decimal places. But this is what your Desmos should look like. So pause the video now and plug it in and see if you get this graph. It may not be the same color. And then if you just highlight your cursor over these points, over where it crosses the x-axis, you will find the same zeros. So I would say as my answer, x equals -1.643 rounding, 1.979, but then that gets rounded up, so I would say 1.980, and then 9.663, and those three should be my answer for example number 11. All right, example number 12, find the zeros of f of x equals log base 2x plus 121. So pause the video now, try this one on your own. Remember how to do the custom log. This is what your Desmos screen should look like. So we should get an answer of x equals 0.432, and that's going to be our answer for example 12. All right, number 13, finding intersection points. Find all values of as decimal approximations for which g of x, this equation here, equals 5. And so I would literally make it as simple as possible and type both of these equations into two separate lines in Desmos, and then find the intersection points, and you're looking for the x coordinates. Obviously, because the y coordinates are going to be 5, so that's probably not going to be your answer. This is what it should look like here. So notice how I typed in both equations verbatim, even with that g of x part. It will always work. And then we're going to get our answer of x equals negative 1.235, 1.413, and then 9.822. That should be our answer for example 13. However, watch out. I've seen countless students, even this year, on your tests, on your semester summatives, last semester, they would just plug 5 into the function and evaluate it and then get the wrong answer. So please do not do that. You are finding where is this equal to 5, not what happens when you plug 5 in. So it's a little bit different than the very first question. So just be kind of cognizant of that. All right, number 4, this is talking about the end behavior. Here, remember, there's 4 different types of functions. There's polynomial, there's rational, there's exponential, and there's logarithmic. You'll see one of these 4, so you'll need to memorize the rules for all 4 of these. However, as a last resort, you will always have Desmos to rely on. So if you don't know the end behavior, just graph it and look at the end behavior, right? If you see a graph that goes like that, we can write this end behavior pretty easily, right? The limit, as we'll call this g of x, because that will be always the function you're talking about. As x approaches infinity of g of x, this is going to infinity, right? So end behavior is going to be pretty easy to see in Desmos, but the rules are still important to always have. So remember your end behavior rules, but more importantly, remember limit notation. So I will take off points if you don't have limit notation. So you need 4 parts. So like this limit here, I'll go over all 4. The first one is you need your limit statement. So the limit as x goes to the left or the right. If it goes to the left, it's going to be negative infinity. If it goes to the right, it's going to be positive infinity. And it will ask you which one it wants, whether it asks whether it increases or decreases without bounds. Then you need the function you're referring to. Every single year I've seen, it's always been g of x, and the question will state what function. You'll need an equal sign. That shouldn't be too hard to remember. And then you'll need your answer. So whether it's positive infinity, whether it's 1/3 or 0, you're going to need that as well. So let's start off here with polynomial functions. Basically, these are the 3 steps that we want to work on to determine the end behavior of polynomial functions. So let's just say I give you a really basic one. We'll go negative 0.7 x to the 7th, right? What will that end behavior look like? So step 1, determine if your function has an even or an odd degree. That's going to be the highest exponent you see. So here, this is going to have an odd degree. And then determine if your exponent has a positive or negative leading coefficient, which is the number next to your highest term. That's going to be negative in this case. And then take your answers, which is negative and odd, and match it with one of the 4 most basic functions here. So it's either going to be plus or minus, positive or negative, and then x. And if it's an odd degree, right, the most basic odd number is 1. And if it's an even degree, the most basic odd number is 2. So those 4 graphs are going to be what your end behavior will look like. So again, if I have negative 0.7 x to the 7th, that's going to mimic negative x to the 1st, which is right here. This is the graph of y equals negative x. So I would say my 2 limit statements is, let's just call this function g of x, right, for the time being. I would say this equation, g of x, will have the end behavior of the limit as x approaches negative infinity. So as we decrease without bounds of g of x, this is going to be going to infinity, and the limit as x approaches positive infinity of g of x, as we go to the right or increase without bounds, this is going down, so it's going to negative infinity. And that's going to be how I would answer that question there. Now write both limit statements for the following polynomials. So pause the video now, try this one, because I'm about to go over the answers. So here we have a negative leading coefficient, and then we also have an even degree. So this is going to behave like negative x, an even number squared. That's going to be like this. So let's write our two limit statements. This is f of x also. So the limit as x approaches negative infinity. And then let's also write the right-hand one as well. The limit as x approaches positive infinity for our function f of x equals, and now here as we go to the left forever, this is going down, so that should be negative infinity. And as we go to the right forever, this is also going down, so this is also negative infinity. So both of these would be our correct limit statements for A. For B, here we have a positive leading coefficient and an odd degree. So that's going to behave like y equals positive x to the first. So like this. And then the end behavior is going to be, I'm just going to start by writing both limit statements there. So negative and positive infinity. Here, notice it's g of x equals, and then as we go to the left, this is going down. So this should be negative infinity. That's our first one there. And then as we go to the right, this is going up. So this should be positive infinity. And that's going to be our limit statement there. So that's 14a and b. Now for a rational function, the rules are going to be a little bit more complicated. So it's kind of like a flow chart where you're going to have to follow different sets of rules based on what type of rational function it is. So the first thing you only care about is going to be the leading terms of any rational function. So let's say you have like a leading term of x to the 6 over a leading term of negative 3x cubed, right? You're going to classify your function as either top, bottom, or equally heavy based on the degree in the numerator and the denominator. In this case here, for that example that I just came up with, we have 6 over 3. So this would be a top-heavy function, and that's like the set of rules that we're going to use to find the end behavior of that whole rational function right there. So let's take a look at the three sets of rules once you have your function classified. So if the function is top-heavy, like this rational function is here, we see, x cubed over x to the first. First thing you're going to do is take your leading terms, so that's 4x cubed over negative x. Then, because it's top-heavy, you're going to simplify that as much as you can into a polynomial. So we can cancel out maybe an x from the top and the bottom, and 4 over negative 1 is just negative 4x squared. Here, then this polynomial, the end behavior of this polynomial will behave the same as the end behavior of that whole rational function. So here you have a negative leading coefficient and an even degree. So that's going to behave like y equals negative x squared. So like that. So our two limit statements should be the limit as we go to the left, this goes down, and as you go to the right, this also goes down. Here, this is nice because it is in factored form. However, if your equation is not in standard form and it is in factored form, you are going to want to factor or FOIL it out to get it into standard form. All right, if the function's bottom heavy, this one's a little easier. The limits both sides will go to 0. So for example, if you have 4x cubed over negative x to the 7th, right? 7's bigger than 3. So the two limit statements will be going to 0, and there actually will be a horizontal asymptote at 0 then. So what that would look like is you may see something, this isn't going to be perfect, but you'll see a horizontal asymptote at 0, and then the function will approach 0 from both sides and get closer and closer to it. All right, and then if the function is equally heavy, this is the case that you would probably see, I would say, on an exam, but again, anything's fair game. Here, both limits will be the ratio of the leading coefficients. So we'll take our leading coefficients, which is going to be 4 and 5 in this case, and that's going to be your two limit statements. So this is why it's hard, because if it's, an extended decimal, Desmos will just give you that decimal and not the exact answer. So in this case, the limit as x approaches negative infinity is 4/5, and the limit as x approaches infinity, positive infinity, would also be 4/5. That's going to be pretty much the same. So let me draw what that could look like, where you also have a horizontal asymptote at, this is y equals 4/5, and then what it would look like graphically could be the same thing, where it will approach that number from both sides as well. Right? All right, so for example 15, we want to write both limit statements for these rational functions. So for a, taking the leading terms, I see x cubed and 8x squared. I don't care about anything else, so x cubed over 8x squared. I see that this is going to be top heavy, so what I'm going to do is simplify this as much as I can. Here I can cancel out an x squared from the top and the bottom to just give us x, and then this is 1 over 8, so I'm going to put that as my leading coefficient. Here we have a positive 1/8, and it's to an odd degree, so positive odd is going to behave like y equals just x. This end behavior is like that. So that should be our two limit statements there. So the limit as x approaches negative infinity and the limit as x approaches positive infinity for f of x. So let's write that in for both of those. Here, as we go to the left, this is going down to negative infinity. And as you're going to the right, this is going up to positive infinity here. So that's going to be our answer for example 15. For this one here, for B, we have 4x cubed as our leading term and 7x cubed. This is equally heavy, so this will simplify to 4/7. There will be a horizontal asymptote there. You don't need to know that for the end behavior, but both end statements both limit statements for the end behavior will go to 4/7. This is why, in this case, if you try to plot this on Desmos, it's pretty hard to identify that 4/7 is the fraction that you're going towards as you get really, really big x values and really, really small x values as well. So our two limit statements would look like the limit as x approaches negative infinity of g of x this time is 4/7, and then the limit as x approaches positive infinity of g of x is also 4/7. Both of those should be our answer for 15. So now we have exponential functions, and this is going to be pretty easy. What we see here is we're always going to see an equation in the form of a times b to the power of x. And the first thing you want to ask yourself is b going to be greater than 1? That will be exponential growth, or less than 1, where it's exponential decay. If it's greater than 1, then that means you're multiplying constantly by a number that's greater than 100%, or 1. If it's less than 1, let's say b is like 0.5, you're multiplying that your starting value by 50% every time you increase x by 1. So you're obviously cutting it down. That's why it is decreasing there and then increasing here. In this case, both limit statements are fairly easy, right? One will always go to positive infinity, and then one will always tend towards 0. So that will always be the case there without any vertical translation. Obviously, right, if we have an equation where it shifts up 2 units, instead of going towards 0, it's going to go towards 2 as a y value. And then the only other thing that you may need to worry about is if a is positive or negative. In both of these cases, a is going to be assumed to be positive for growth and decay. But remember, if a is negative, let's say I make this negative 3 times 0.5. That negative sign is a vertical reflection So your graph is going to be the same as this, except it's going to be the reflected version over the x-axis. So this is where a is less than 0, but b is still between 0 and 1. And this graph is where a is less than 0, but b is still greater than 1 there for those two graphs that I just drew. Right, so let's try example 16, write limit statements for the end behavior of the following exponential functions. Here we see our b value is greater than 1, right? It's 5. And our a value is positive. That's all we really care about. We don't care that it's less than 1. It's just positive. So this should be exponential growth. So our limit statement would be the limit as x approaches negative infinity for the left and the limit as x approaches positive infinity for the right of f of x. So get the correct function name. If you use the correct or the incorrect function name, you will not receive any credit. And then this is going to be, as you go to the left, this is tending towards 0. And as you go to the right, this is going towards infinity. Taking a look here, we see a growth, right? 3 is bigger than 1. So it should behave like this. But then I see a negative number. So it really should be that, but reflected over the x-axis. And I'm going to erase that original one because this is what the graph should look like here. Our two limit statements would then be the limit as x approaches negative infinity for the left-hand side of h of x equals, and here remember, one side will always tend towards 0, so this is going to be 0. And then the limit as x approaches positive infinity of h of x, this is going down towards negative infinity. So that should be our answer there. And then g of x is a positive a value, so that's nice. And then our b value is 2/3. That's less than 1. So that is just going to be a case of exponential decay. So let's write that out as well. The limit as x approaches negative infinity of g of x. This is going up, right? As we go to the left, this is going up to positive infinity. And then here, the limit as x approaches positive infinity of g of x is going towards 0 right there. So that should be our 6 limit statements for example 16. All right, now logarithmic. For a logarithmic function, it's only half as hard because instead of 4 graphs like the exponential, there's only 2. Basically, just memorize the left one. Here, a is assumed to be positive, and then b is assumed to be greater than 1. B will always be greater than 1. And this will be in the form of like f of x equals a log base bx. And then the only thing that could change is what happens when a is negative. Remember, a being negative means a vertical reflection over the x-axis. So here, where a is positive, right? As soon as a becomes negative, you are going to take this graph and you are going to flip it over the x-axis. So that would look like that. And that should be your new shape of the graph, which is what we have there, where a is negative, but b is still greater than 1. Now, keep in mind, because it's a logarithmic function, the left-hand limit statement will be restricted because it's not going to the left forever, right? Because you can't have negative values inside a logarithm because you can't take the log of negative numbers. So our domain is restricted from 0 to infinity. So here our limits, our left-hand limit statement is the limit as x approaches 0 plus of whatever function equals and then whatever the limit statement is. Here it's going to negative infinity, positive infinity, and negative infinity there. So let's take a look. Just know if a is positive, it's just increasing, and then that's really it. And then if a is negative, you just flip it. So write the end behavior of the following log functions and limit statements for a. Here, as x approaches 0 from the right-hand side, this is going to negative infinity. And then for the right side, the limit as x goes to positive infinity of f of x, this is going to positive infinity. So that should be our answer for 17a. 17b, as we approach 0 from the right-hand side, this is going up. towards positive infinity. And then the right-hand limit statement would be the limit as x approaches positive infinity for h of x. This is going down to negative infinity. Now for g of x, when we have our equation, 2 log 3x, this is positive, so it should be an increasing function like this. And so the limit as x approaches 0 from the right-hand side is going down towards negative infinity. And then the right-hand limit would be the limit as x approaches infinity of g of x, and this goes to positive infinity there. So that should be our answers for 17. Now here is how the question will be worded every time. Determine the end behavior of g, which is, remember, the equation. As x either increases or decreases, it will have one of those two words without bounds. Increases means you're writing the right-hand limit statement, and then decreases means you're writing the left-hand limit statement. Express your answer using the mathematical notation of a limit. That just means a limit statement, right, in limit notation. So just remember, if it increases, it means as x approaches positive infinity. If it decreases, it means x approaches negative infinity. Now I will say, on your semester summative and the AP exam, the way I score it is if you write both limit statements. That is fine. I will not take off points, but both need to be correct. If you get the one that I ask for correct, but then you add an incorrect limit statement, your whole answer will be marked as wrong. So just really be careful on that. That's why I say always stay to the safe side. And why add more work for yourself? Only just write the one limit statement it asks for. So just be careful for that. All right, let's try two more examples. Here, I will actually show you the photos in Desmos zoomed out. So I would always say zoom out a lot so you can get a really good grasp. But this is what it should be. And then let me work through it with the rules, and then we can also just fact check with Desmos. So here, determine the end behavior as x increases. We know this is a polynomial, so look at our leading term. We have a positive leading coefficient, and then 3 is our degree, so an odd degree. So this should behave like y equals x. And then as we increase, this is just going to the right. So it's a limit as x approaches positive infinity of g of x. And then this is going towards positive infinity, so that would be our answer. There's no work you need to show. Here we also see that as well, right? As x goes to the right, this graph is going up forever. So you can see that limit statement in action if you really wanted to. For example, 19, here we have a rational function. Taking a look there, we have a top-heavy function because our leading terms are x squared and x. Because it's top heavy, we're going to simplify it to just x, and then the end behavior of this polynomial is like y equals x. So that's our end behavior, and we're looking for the end behavior specifically as x decreases, so as x goes to the left. So the limit as x approaches negative infinity of g of x equals, and then this is going down forever, so negative infinity there. And that will be our end behavior there. So you may need to zoom out, right? We do see a vertical asymptote, but that has no effect on the actual end behavior. So really don't let that, kind of confuse you or scare you off from looking at Desmos. Worst case, you just go back to these rules that you hopefully will have memorized and can use them accordingly. All right, the fifth type of question that you can see is going to be a two-part question. It's determining the type of function from a table. It will only be a table, not from a graph. You have had tons of practice with this. So this is like those kind of cookie cutter statements that you kind of need to memorize all the way from the very first lesson that we did. So it will be worded like this. Use the table of values to determine which one of these four. So it will always have those same four options. Is going to be basically what type of function the table is. Here, you're just going to give your answer for part 1 of the 4, and then part 2 is where you give your reasoning, and then here you need to refer to values in the table or reference the table specifically. So here's an explanation for each one. For linear, right, this is what it could look like, where your x values are going to be the same, so +1, +1, +1, or as we say, your input values are equally spaced, right? Over equally spaced input values or equal length input values is typically how we start our answer. And then our y values we see here are +1, +1, +1. Here, this is the first difference is what we'll call that. And the first difference is constant, meaning the same, right? 1 is the same as 1, which is the same as 1. So our explanation is over equal length input value intervals. So you need to talk about your x and your y values. Your output values, so your y values, have a first difference of +1. So there, you talked about your x values. That's the first thing I'm looking for. Then you talked about your y values. That's the second thing. And then you said they had a first difference, so that's talking about your y values. And then you also referenced the table specifically and showed how you looked at the actual numbers versus just memorizing a random cookie cutter answer by giving that +1. So showing that you actually found that first difference and it was +1. All right. Now for quadratic functions, your input values will still be equally spaced. So here, +1, +1, +1. But now your output values will have a constant second difference, right? It'll make sense. The degree is 2 for a quadratic function. So your second difference should be constant. If we take a look here, we see +1, +2, +3, right? Our first differences are not constant. They're not the same. But if we go one more deeper, +1, +1, our second difference is constant, right? They're both ones. And as long as you have two of the same number, that's enough to infer it. Like we wouldn't need, you wouldn't need to have a third number here to prove that, right? So here, over equal length input value intervals, the output values have a second difference of +1. This would be enough there. Here you're talking about the x values, so that's good. You're talking about how the y values have a second difference, and then you're saying what is that second difference. So all three of those would be the three things that I would be looking for on an AP exam or on your semester summative. All right, the next two that you could come across is going to be a little bit easier. First is exponential. This is where your input values are equally spaced. So here, +1, +1, +1. I like to think of exponential and logarithmic. Your input values are an addition rule, and then your output values change proportionately, which is going to be represented by a multiplication rule. So here, because it's growing exponentially over time, we see that it's not +6 plus 16 plus whatever that number is, right? It's going to be times 3, times 3, times 3. And so you'll see if the numbers grow really big, really fast, it's probably going to be an exponential function. So some of this is just kind of intuitive on figuring out what type of function it is. But when you have a multiplication rule, we want to use the words change proportionately. So our explanation is going to be over equal length input value intervals. That will talk about our x value. The output values, so your y's, will change proportionately. I need to see this word proportionately in your answer if it is exponential by a factor of 3. So I need to see what the factor is. So proportionately and factor are going to be the two keywords here. And then of 3, 3 is your multiplication rule. So I need to see that rule as well. All three of those parts are going to be what I'm looking for exponential. And then logarithmic, remember, logarithmic functions are just the inverse of exponential functions. So your inputs and outputs should essentially switch. So your input values now will change proportionately. This will be the only time your input values are not equally spaced. So here we take a look, we see times 2, times 2, times 2. And now your output values are an addition rule, are equally spaced. Here it's plus 5, plus 5, plus 5. And so our explanation to part 2 is going to be over equal length output value intervals, right? So here the part that's equal length is our y values. The input values change proportionately by a factor of 2. So it's basically going to be the same thing as exponential, but you're just going to switch the words inputs and outputs and still make sure the numbers are correct, right? So here the factor is 2 because 2 is our multiplication rule, not 3 like in the exponential example. All right, so example 20. You use the table of values to determine if f is best modeled by linear, quadratic, exponential, logarithmic, and then explain why. So here I'm taking a look and I see plus 1, plus 1, plus 1, plus 1. So I can rule out logarithmic right away, just because the inputs are equally spaced. And now let me take a look at this. I don't really see a nice multiplication rule, so I'm probably going to eliminate exponential. But if I get that it's not linear or quadratic, I'll go back to exponential as a possible answer. Here, though, I see minus 1, plus 1, plus 3, plus 5. So they're not the same, so you can eliminate linear. And then taking a look at the second difference, though, from negative 1 to 1, that's plus 2, plus 2, plus 2. So that makes me very happy because I now see a quadratic because the second difference is constant. So quadratic is all you need to write for part 1. You'll get 1 point there, so it should be an easy point. Part 2 is where we give our reason. So here I always like to start, if it's linear, quadratic, or exponential, with over equally spaced inputs the outputs have and then here I'll just say second difference of plus 2. So here I talked about my x values. Here the outputs have a second difference. I talked about how my y values are changing. And then I talked about the specific number. So all 3 of these would be good enough. I would get plus 2 points there, making me very happy. All right, and then the 6th type of question that you could see, so you'll either have a what type of function is this, or is this function invertible type question that will be worth 2 points. So this is also a 2-point question. Here, you're basically going to be asked to determine if a function is invertible or not, meaning if the inverse of a function is actually a function. And there's 3 different ways that they can ask this, or anything that's like similar to this. Is determine if an inverse function can be constructed, if it has an inverse function, if it's invertible, right? And so those 3 things all mean the same, so they're all equal or synonymous there. So basically what you are going to be looking for is to determine yes or no even. You are going to, on a graph, perform the horizontal line test, right? So if the horizontal line test fails, then when you take the inverse of the function, the vertical line test is going to fail as well. So that's how you can tell graphically. But what you're really doing is looking to see if 2 x values on the graph, right, give you the same y value. Because if that occurs, then the function is not invertible. And that's not just for a graph, but for a table as well, right? So if you see a table where I'll make up an example, 1, 2, 3, 4, 5, 6, 7, and then 6 here, this function is not invertible because there's 2 x values that give you the same y value. So that is how you determine either yes or no, if it is 1 to 1 or if it isn't, meaning every x value corresponds to one and only one y value. For part 1, all you have to do is just say yes or no. Part 2, you'll give a reason based on your answer, and so you need to talk about two things. One is just the definition of what does it mean to be invertible. Here, I've had you guys memorize the function is or isn't 1 to 1. Obviously, if your answer is yes, then it's going to be is 1 to 1. If your answer is no, it's going to be is not 1 to 1. Or you can say the longer answer. All right, there are output values of usually it'll be F or G. I think it's usually F that are or aren't mapped from unique input values. And then you'll have to reference a table or graph. So if it is not invertible, you will have to give specific points that break that rule, the horizontal line test. And if it is invertible, you have to state whether it is strictly increasing or strictly decreasing, right? Because if a function is strictly increasing and it only goes up, there's no point where it's going to circle back and break that horizontal line test. Same thing if it's strictly decreasing there. All right, so here's a chart with the different answers that you can come across. So let's take a look at some of these. For the first one here, this table would be considered invertible. It's 1 to 1 as it's strictly increasing, right? There's no x value that gives the same y value as another x value, right? 1 goes to 0.5, 2 goes to 1, 3 goes to 2, 4 goes to 4. And so here, I would say it's invertible because it's 1 to 1. That talks about the definition. And then here it's strictly increasing because it's exponential, right? As we saw, times 2, times 2, times 2. And so you probably won't see this, but if you do, that's how I would give the explanation. If it is not invertible, here you would say because it is not 1 to 1, so that will talk about the definition. And then we need to give the 2 points that break the rule. So 1 comma 2 and 3 comma 2 have the same y value. That will give points, and so both of those would be good enough there. For number 3, this graph is invertible. So it's 1 to 1 and strictly decreasing, right, as it's a linear line. So that would be enough there. And then if it's not 1 to 1 and it's a graph, here we would say it's not invertible because it's not 1 to 1. And then these 2 points, negative 1 comma 3 and 1 comma 3 have the same y value. There's multiple points you could go with. You could go with 0 comma 2 or 2 comma 0 and negative 2 comma 0 as well have the same y value. So any 2 points that you want to use is fine for that last example. I just would typically go with integer coordinates though, if anything. All right, so let's try example 21. Determine if an inverse function can be constructed. Here I would say no, because I see that those 2 points, 2 comma 4 and 5 comma 4 have the same y value, and then give a reason. So I would say it is not 1 to 1 as 2 comma 4 and 5 comma 4 have the same y value. Right, so that would be enough there. Let's move on to 22. This was actually a question from the 2024 AP exam. So determine if f has an inverse function. Here, I would say definitely doesn't pass the horizontal line test, so I would say no. And then I would say it is not 1 to 1. And then here, looking for integer coordinates, there's 3 points there, but you only have to give, 2. You could give all 3 as negative 3 comma 1 and 0 comma 1. We'll give all 3, and 3 comma 1 have the same y value. That would be enough to get full credit for here, so you get 1 point for saying no, and then you get 1 point for referencing at least 2 points there. So that would be our answer to 22. All right, if you guys have any questions, please come see me in office hours, and I will see you guys later. Thanks.